Okay, we should be done, right? We've explained how to do deductive reasoning. The only problem is that deductive reasoning, although it's great and we always end up using it, it has some limitations, so we can't use only it. The limitation of deductive reasoning is garbage in, garbage out. It's good at going from premises to conclusions, but the quality of deductive reasoning the quality of any reasoning relies on the quality of your premises. And last time, when we were constructing deductive arguments, we just assumed that our premises were 100% true. They were completely known facts that were and all A's were definitely B's, no exceptions, and no doubt either. The number of things that we know for certain that much just isn't all that big. So if we just did deductive reasoning, we wouldn't really get that far. What happens when we apply syllogisms and make inferences, but when we're not so sure of the premises? We could do it, but we wouldn't be as sure of our conclusions as we are in deductive reasoning. So we give the application of syllogisms to less than perfectly certain premises, we give that a different name: inductive reasoning. In deductive reasoning, the conclusion is pretty much implied by the premises, and it's just a matter of thinking about the premises and rearranging them, doing some substitutions until you have them rearranged into the conclusion. In inductive reasoning, we make more of a leap of conjecture, going beyond what's implicitly stated in the premises. That makes inductive reasoning less certain than deductive reasoning, but it does allow us to go further. One other difference is that deductive reasoning is generally either completely true or completely false. A syllogism is either valid or invalid. There really isn't any middle ground unless we want to do liar paradox stuff. So the validity of syllogisms is binary, either all good or all bad. And when we worked in our examples of deductive reasoning, the premises were either all true or all false. So truth was easy to ascertain. But what if we're not exactly sure of the truth of a premise? Maybe it's not determined. Maybe no one knows that fact yet. We think we know, but what about situations when we have trouble determining the truth of premises, and we're trying to reason even further from uncertain premises? Then the conclusions that we reach are a lot less certain. It could be, and so inductive arguments aren't really classified into sound, valid plus true, or unsound, valid but not true, or invalid. They're more classified into strong or weak, or invalid. Assuming that the syllogism is fine, then they're strong or weak, depending on several things. First, the truth of the premises, but also the relevancy. How good is a syllogism? Inductive reasoning is a lot fuzzier, more of an analog kind of logic than deductive is. Is it reliable? So far, it doesn't sound very reliable. We'll work on that a little later. Why do we need to bother with it at all? Because real life doesn't involve all that many perfectly solid facts where you can just rearrange the information and get to the conclusion. That happens sometimes, but sometimes we're not so lucky. So we're going to try to start over again. We have deductive reasoning, but we're saying we need something else. How do we do inductive reasoning? It's really reasoning by analogy. Okay, another word we don't know, analogies. The simplest kind of induction is called enumerative induction, which is reasoning by following an example. I saw 1A, and that A was also had feature B. And if we extrapolate that, maybe all A's have feature B. When we make that extrapolation, we're starting to reason by analogy. Can we make that conjecture that all A's are B's just because we saw a few A's that are B's? Sometimes we can, sometimes we can't. That's what this chapter is all about. One idiom, recently coined idiom in English, is the Black Swan. It was when it's an example of induction sort of failing us. For a long time, people thought all swans were white, because every swan they had ever seen was white. And these people were in Europe. All the European swans were white. So a black swan was an imaginary animal. It was a metaphor for a thing that doesn't physically exist. We can put those words together and so have the term a black swan, but it doesn't exist. And so in European literature, that's what a black swan meant. But then, more recently, Europeans traveled all the way to Australia, other side of the world, and there are black swans there! Actual physical swans that are dark colored. Like, well, guess we need to change that metaphor. They thought that a black swan was impossible, and their inductive reasoning from every swan that they'd ever seen legitimately led them to the conclusion that there are no black swans. But then they went to the other side of the world and ran into a black swan. So I guess the black swan, the physical animal, was a black swan, the metaphor. An unexpected thing that couldn't have been planned for. Or actually, you did some planning, and you were sure that you didn't have to worry about this thing, but then the thing happened. So, inductive reasoning is not perfectly reliable. Whereas deductive reasoning, assuming it's valid, assuming premises are true, your conclusions are 100% guaranteed. And dealing with the uncertainty and weakness of inductive reasoning without entirely running away and not doing it at all and limiting ourselves to deductive reasoning is what statistics and science are all about. So, the most fundamental task is to judge the quality of an induction. The greater the sample size, the more reliable your conjecture are. If you've seen 1,000 A's and all 1,000 of them had property B, you're probably a little safer in saying all A's in the world have property B than if you'd only seen one A and made that conclusion. Black Swans aside. However, a lot of times in real life, you will have counterexamples. Not all A's will be B's. But what if we're trying to say that most A's are B's? The greater the proportion of A's that are B's in your sample to counterexamples strengthens your conclusion that most A's are B's. But then you're doing sampling and you hope your sample is a real reflection of all the A's in the world. Now we're getting into statistics. We'll do statistics in the next chapter. It's important, but we'll get there. Also, you don't want your sample to be biased, and you don't want too many counterexamples. So there's some technical stuff in doing a good job of reasoning by analogy. That technical stuff is basically statistics and the foundations of science. We'll get to that a little later. But first, the criteria for good analogies. Because making good analogies versus bad analogies is the difference between inductive reasoning being unreliable, stick just to deduction, and inductive reasoning being pretty good, let's keep using it. So what are the criteria? Well, relevance, number of instances of the premise, variety of instances in the premises, disanalogies, and modesty of the conclusion. Okay, and now we just have to define those. Relevance. Judging relevance is a bit of a judgment call. So we saw two things being similar in one way, and we're making the conjecture, the induction, that they'll also be similar in another way. You're thinking those similarities are linked. That's an analogy. Or analogical reasoning. So let's say we have two laptops and we know the reliability of one laptop and we're attempting to make a hypothesis about the reliability of the other laptop. Tom's laptop has feature A. Therefore, I think that Mary's laptop, or Mary's laptop also has feature A. Tom's laptop has feature B as well. Will Mary's laptop also have feature B? That's a judgment call that depends largely on the relevance, depends on whether or not A and B are correlated, or the relevancy of A to B. So let's put some real nouns in there instead of just letters. Tom's laptop is a Toshiba. Toshiba tends to make very reliable computers. Maybe they do, maybe they don't. Just go with it for the sake of argument. Mary's laptop is also a Toshiba. Same brand. Will Mary's laptop also be reliable? Yeah, probably. Like, not certainly, but yeah, probably. The manufacturer feature is relevant to our conjecture about reliability. Now let's make a conjecture about reliability off of a different similar feature, different analogy. Tom's laptop is black. Tom's laptop is reliable. Mary's laptop is black. Will Mary's laptop also be reliable? I don't know. Most laptops are black. There are reliable black ones, there are unreliable black ones. I really don't know. A color to reliability analogy is a lot weaker. How do we judge that? Well, judging causality can be complicated. We'll deal with that at the end of the science chapter, the one after this. But in this instance, the main criterion would be the imaginability of a plausible mechanism. Reliability depends on good manufacturing processes. Good manufacturing processes correlate by company, by manufacturer, but I really don't see how color would affect manufacturing processes and reliability. One of these things, I can imagine a mechanism that's plausible. The other, I can't. So for one of those analogies, it's reasonable. It's a strong inference, strong induction, manufacturer to reliability. But for color to reliability, not so much. Okay, so we have relevancy of the criterion. That's probably the hardest one. Now, a few more others that are easier, but still, we don't want to overlook them. Number of instances in the premises. Let's say we're wondering how long it'll take Bob to get to work tomorrow. I don't know. How long did it take last time? How long was the bus ride? 40 minutes. Just because yesterday's was 40 minutes, does that mean today's will be 40 minutes? It's a rough guide. It's not worthless, but not very strong. What if, instead of going off of 1 day of history, we went off of 5 years of history? Every day for the past 5 years, it takes about 40 minutes. Well, if we have 5 years of data, a large number of instances in the premises, that is a much stronger analogy than going off of just 1 day. Also, one thing that matters is the variety of the instances. Does it, those times when it took 40 minutes, was it just on sunny days with little traffic? Or is it 40 minutes no matter what the time of day, whether it's rush hour or not, no matter what the weather is? If it's 40 minutes always, despite a bunch of other variables, despite a bunch of variety and chaos in the historical premise examples, then you would be more sure about a prediction about tomorrow. Because we don't really know what tomorrow's crazy variables will have. Maybe it'll snow. Maybe there will be a lot of traffic. In the historical premises, have we seen snow and traffic before? If yes, we can still predict about tomorrow. If no, well, if tomorrow has snow or traffic, then we're in an unprecedented situation. We don't really know. Or we're not even really confident. Fourth criterion would be disanalogies. It's pretty much the flip side of the variety of instances in the premises. If tomorrow is going to be different than all the other days, then it's hard to legitimately extrapolate from the other days to tomorrow. Let's say Bob had taken the bus every day for a month, and it was always 40 minutes. But tomorrow is a holiday, and Bob's never taken his commute on this holiday before. Well, his experience in that past month might not be an especially reliable guide to the unprecedented instance of this holiday. If he had taken the bus for years and had seen this holiday in previous years, then he maybe knows how long his commute will take on the holiday. But if tomorrow's situation is unprecedented, holiday that he's never commuted in before, that would amount to a disanalogy between the previous data, the premises, and tomorrow, the thing we're trying to make a conclusion about. And the last criterion is the modesty of the conclusion. Let's look at the probability of our prediction being right. That can be very much affected by what prediction exactly we make. How long does the commute take, Bob? About 40 minutes. What do you mean by about? Okay, well, someone asked me how long the commute is. If I say the commute is exactly 40 minutes, it takes more than 39 and less than 41. It's always 40 point something. That's a very specific prediction. However, if I said, it takes between 30 and 50 minutes, a much bigger range, it's sort of a different likelihood of me being right. If I say it takes somewhere between 2 seconds and 2 days, that's definitely true. I'm definitely right. It might be useless, it might be tautological, but I could make my prediction so broad that it's useless, but I'm 100% right. At the other end, I could make my prediction so specific that if the bus is early or late, even by a few seconds, I'm technically wrong. I said it would take exactly 40 minutes. Oh, it took 40 minutes and 5 seconds. 40 minutes and 5 seconds is not 40 minutes. You were wrong. The probability of a prediction being technically correct depends a lot on how specific the prediction is. That's sort of obvious, but that amounts to one of the most basic rhetorical norms in science. Scientists tend to be very modest about their conclusions, mostly because they don't like being wrong. So to avoid being wrong, they tend to give themselves a larger error range. And you see that especially with medical claims. Because in medical claims, if you say something, in some countries, if you say something and it's not proven to be true, you can get in large amounts of trouble. So let's say someone thinks they're going to get a cold, but they take a medicine and they don't get a cold. Did the medicine prevent the cold? Maybe it did. Maybe it was just coincidence, though. Maybe they weren't going to get a cold anyway. And so labels for medicines tend to not make very specific conclusions. They do some tests and a lot of inductive reasoning, but they try to not have very specific conclusions like Zicam reduces colds. That would be a very declarative, somewhat specific, or Zicam prevents colds. Declarative, specific conclusion. Well, someone might take Zicam and then think they're completely immune to colds and not bother with basic germ precautions. Oh, they got a cold even though they took Zicam. You gave them a false sense of security. Bad. So, scientists and the medical claims that are based on science, which is basically a lot of inductive reasoning, tend to say things like, the results of this study suggest that Zicam probably reduces the frequency and severity of colds. They'll put a bunch of qualifying phrases in their statement so as to give them more room for error, which in formal terms that would be increasing the modesty of their conclusion. Of course, a conclusion can be so modest as to be useless, like predicting that Bob's commute will take somewhere between 4 seconds and 4 days. Yeah, it's probably right. Doesn't help us, though. And so, in doing our inductive reasoning, we need to strike some balance between being too specific, and you are close, but you are wrong, and being too broad. Yeah, you are right, but your conclusion was obvious and useless. And how to do that well is what statistics is all about. That's why statisticians are highly paid individuals and scientists are involved in a respected profession. It's hard, but that's how society advances. It lies on a foundation of critical thinking. Without critical thinking, statistics and science just go badly awry. But we're going to now get into statistics and science, how modern society progresses and keeps getting better and better. Okay. Talk to you again soon.